Hello guys, welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at the same two-block pulley system setup that we've dealt with in the past, but now the new thing here is that we have this 200 Newton force to the left, and we're going to solve this with energy, looking at the energy conservation side of things. Okay, I'm happy to do another video in the future in which we do this just looking at Newton's laws, and we can do that. That's perfectly fine. But on this one, we're looking at energy. Because we're ignoring friction, what we expect is that this block is going to be pushed to the left because of that 215 Newton force there, which means that this guy is going to go upwards, right? So let's go ahead and read problem statement and solve this. And what I'm going to do is I'm going to solve this in two different ways, okay? The first way, I'm going to do it a very intuitive way, which is going to be fast and straight to the point. And then we're going to do a more general way. And you guys can stick to the end if you want to learn the more general way. It's up to you. So problem statement reads, the system shown is at rest when a constant 250 Newton force is applied to block A, neglecting the masses of the pulleys and the effect of friction in the pulleys and between the block A and the horizontal surface determine the velocity of block B after block A has moved 2 meters and the tension in the cable. Okay, so a couple important things already. The system is at rest initially, so there's no kinetic energy whatsoever from A or B. Like I said, we're going to be ignoring the friction and the masses of the pulleys, so no friction there. What else? There's no friction between the horizontal surface, so there's no friction here between A and the surface. And the reason why we're tackling this mainly as a energy problem is because we have a force being applied over a distance of 2 meters. We know that force times distance screams energy, right? So what we're going to do is the same exact thing we've done from the start on this problem, right? So I'm going to break this and do this in green. I'm going to break this the center pulley here over here. I'm going to create two axis systems, two axis lines, I guess, two axis that we'll use as our origin, and then I'm going to create a vector that leaves from this axis that I've created and goes to wherever B is. And likewise, I'm going to create a vector that leads from our axis systems and go to where A is. I'm going to call that XA. Okay, so these are vectors. Okay, and just like before, if you note, if we sum up vector A plus 1, 2, and 3 of vector B, we're going to have a constant, which is the length of this rope. And we can sum up this other bit, and it's also going to be a constant regardless, right? Because this cable, right? This cable has a constant length. It's not stretching out or being compressed in any way. So first of all, 3 of my YB plus 1 of my XA plus whatever, if you want to consider anything else, is a constant. So therefore, if I derive this, I'm going to have it 3 times the velocity of B plus the velocity of A has to be nil, right? It has to be 0. And we can do that once again for acceleration if we want to solve it without using the energy approach. Now, note that when we're doing this, it's best for us to write down that we're considering downwards to be positive and leftwards to be positive, even though I know that block B has to be going up, right? So what we expect when we do this is that we expect to get VB as a negative velocity, which indicates it's going upwards, right? Now, the reason I always consider this going downwards is because it's very intuitive for us to have this vector here going from the axis down to my YB, regardless of whether B goes upwards, in which case my YB is going to decrease, or if it goes downwards, in which case my YB increases, right? So check out what's happening. We have the 250 Newton force being applied over a distance of 2 meters, okay? Being very straight to the point here, we're going to just say energy is force times distance. Okay, when I do the general approach, we'll actually integrate it to do it step by step. But here we have a 250 Newton force being applied over a distance of 2, and then Newton times meter, that's a joule, right? So we pretty much have 500 joules. Okay, we have 500 joules, and we have 500 joules to split among 3 things. What are the 3 things? Well, note that once this block here rises, as we expect it to do, we're going to be giving it some potential energy, right? Because it's going to be at a height that's greater than the initial height. Also, because it started to move and we know that a force is going to incur in an acceleration, and that acceleration is going to incur in a velocity, we expect VB to have a certain velocity after the force has been applied for 2 meters, right? Likewise, A, because it's moving leftwards, we expect it to have a velocity A. Okay, so pretty much what we're doing is we're converting those 500 newtons into 3 things: into the potential energy for B, into the kinetic energy for B, and into the kinetic energy for A. Okay, so let's start with the potential energy for B, because whatever is used by this then is going to be taken away from our initial energy pot, if we think it that way, right? We have the initial energy bank there. So how much is B moving? How can we determine that? Well, again, very intuitively, if for every 1 meter that this A moves, we're going to be moving 1/3 of this guy here, then it's only 1/3 of the way it's going upwards, right? So again, intuitively, and I'm going to do this in detail when we do the second approach, okay? So the distance d, let me scrap that. So the delta y that this moves, all right, the delta y is going to be 1/3 of whatever delta x was moved on A, right? And we know delta x was 2, so this is just 2/3, okay? So my b is going to be moving, 2/3 of a meter, okay? 2/3 of a meter. So that means that my potential energy, the gain potential energy, I guess, for B is just going to be the mass of B times gravity times the delta y that we know it's 2/3. So that's going to be, what's the mass of B? 25. So 25 times 9.81 times the 2/3. Okay, and this is acceleration here. This is mass here. So this is force, Newton, and this is distance meters. So Newton times meters, that's a joule as well. So this ends up being about 163.5. 163.5, and that is joules. Okay, so from our 500 joule bank that we had initially, 163 are going to our potential energy. So what is left? So what's left? So from energy left, I'll put left in volts because we know it's not quite that. So it's just 500 minus the 163, so that's 300. So this is 336.5. Okay, so we have 336.5, and we know that that's being converted into kinetic energy, right? So what we're saying is that we have 336.5 joules, which will be equal to the kinetic energy on A, which we know is mass of A, velocity of A squared divided by 2, plus the mass of B, velocity of B squared divided by 2. Cool. So now we have two unknowns with velocity of A and velocity of B, but we know there's a relationship between the two, right? We know here there's a relationship between the two, and the relationship is that VA is just negative 3 VB. So where I have VA, I can sub in negative 3 VB, so I'm going to have 336.5 is just the mass of A, which is 30, minus 3 VB squared divided by 2, plus 25, the mass of B, VB squared, which is the thing I'm trying to find, the unknown in this case, over 2. Okay, so all I need to do is multiply by 2 over there and then solve for VB, which is my unknown. So that's 673. Then I'm going to have 9 multiplying 30. It's 270. 270 plus the 25, 295. So this is just going to be, so VB is just going to be the square root of 673 divided by 295. And that, give me a sec, is 1.51 meters per second. Cool. So that is the velocity of V. So that is answer for 1. Okay. One thing though that we need to have in mind is that this velocity here for B, because we have this, we're taking the square root, right? It can be positive or negative. Positive or negative. So because we have this square situation, it doesn't correct us if we make the wrong assumption, right? So we know that VB should be negative, right? Should be going, because we know V should be going upwards. So we can discard, again, we're doing the intuitive approach, right? So we can discard this one here, and we have that as our final answer, okay? All right, so we've done the first way, which is the intuitive way that I told you. Now let's do a more general one so that there's no mistakes whatsoever. So obviously you can choose whatever you find easier, and the general one is better if you have the time because there's no going wrong with this one. But sometimes you're doing an exam or something and you don't have the time. So let me just quickly put the things that we decided at first. So this is my positive over here. This is my positive over here downwards. Okay, so what I'm going to do now is I'm actually going to do an energy balance considering everything. Okay, oops, sorry. This is supposed to be my ground. Okay, so I'm putting a ground here. So this is our ground. Because before anything happens, we know there's a height, right? There's a height from which B is hanging, height H. Okay, and then what's going to happen is, okay, there are assumptions here. Our B is going to go a bit downwards. So let's just let me put it over here. And what is the difference there? Well, if it's down here now, then this height has changed to maybe this one here. And now this difference here is my delta y. Whatever my y has traveled, that's my delta y. Okay, so I'm just going to leave this now. That's my delta y. If indeed my delta y goes downwards, like we're saying it will, this delta y is going to be a positive number. It's going to be my h minus my yb. If my b goes upwards, which is we know is going to happen, the distance itself is going to be the same. The only difference is this is going to be a negative number. Okay, so regardless of your assumption, this is always going to work. Cool. So what do we have at t0, right? So at t equals 0. So before anything happens, before my force is applied there, what is the situation? Well, we only have the potential energy on B, right? We only have the potential of B, which is mass of B times gravity times that's height h that we found from the get-go, from the beginning. And then after t after, let's call it t after. At t after, what we're going to have the three energies that we talked about, right? Potential energy of B, which now has changed, plus the kinetic energy of B, plus the kinetic energy of A. Okay. And what are we going to do? Well, we're going to say that energy cannot be created or destroyed. Delta H has to be 0. So therefore, whatever force is being applied between the two has to account for the change in energy. Okay, so in other words, let's write it. So I have my energy before, and I have my energy after. So for this one to be equals this one, then we need to put the whatever is given by the force over here, right? So what we're saying is that whatever the energy is afterwards, the situation afterwards, is just the initial situation plus whatever was given to the system, right? Because we can't create or destroy it. Okay, so that's where this has to come from. This gain energy has to come from the force that we're giving to the system, the force times distance, which is a form of energy. Okay, so how do we write this down mathematically? We're saying that the mass of B times gravity, it's a bit too thick, times gravity times h, plus the force being given to the system times the distance d over which this force was applied, has to be equal to the change in potential energy for B, and this is going to be h minus that delta y, right? So this h minus this distance here, which is going to give me my new distance here. So again, all I'm saying here is this difference here is just saying, oh, this height here from my ground to the new point would be is just the original one minus whatever went, how much it went down, right? That's all it's saying. What about kinetic energy? Well, mass of B, velocity of B squared divided by 2 plus mass of A, velocity of A squared divided by 2. Cool. So hopefully you can see that we have on both sides mass, gravity, and h. So this left part here of this fella, so this goes away, and we're left with a negative one there. So my 250 times my 2 meters, which is how much A has traveled, has to be equal to negative mass of B, gravity, delta y, plus mass of B, velocity of B squared over 2. And here I'm already going to switch because we know that VA is just minus 3 VB. So I'm just going to switch. I'm going to have mass of A minus 3 VB squared over 2. Okay, so we're writing the whole energy conservation idea here as opposed to just winging it intuitively. Cool. So what next? Well, we need to find our delta y, and we need to, that's all right. If we have our delta y, then we can solve this right here. So why did I say this is more general? Well, because now for my delta y, what I'm going to do is I'm actually going to make sure of it. So my VB, the velocity B, that's just how my y, my vector y that I created in the beginning, is changing in respect to time, not x, in respect to time, right? So therefore, VB dt equals dy, and therefore if I integrate both sides from 0 to t, from y naught to y, I'm going to have over here y minus y naught, which is precisely my delta y. Okay, now over here I can't really integrate because my VB is changing with time because there's an acceleration, right? So I'm just going to leave that now, and what I'm going to do is I'm going to define my VA, and I know my VA is just how my position on the x vector that I created is changing with time. So therefore, I'm already going ahead and integrate VT, VA dt equals x minus xo, which is this delta x, which is the 2 meters that A has traveled. 2 meters that A has traveled. Yep. Now, what do we know about VA? We know that VA is, where is it? Let me put it somewhere in the corner here. We know that VA is just minus 3 VB, right? We've known that already for a while. So if this is true, then I can substitute where I have VA, I can substitute that in. So this is saying, let's get this bit of this, put it in the corner here. So this is saying that the integral of from 0 to t of minus 3 VB dt is equal to 2. Yeah, and then because 3 is a constant, it can leave the integral, and minus 3 can leave the integral. So this is the same thing as my integral from 0 to t of VB dt has to be equal to minus 2 thirds. Okay, and what have we found out? Well, check out what this is saying. Check out this side here. My integral from 0 to t, vb dt, is equal to negative 2/3. And my integral from 0 to t, vb dt, is also equal to my delta y. Okay, so note how the two sections in blue are exactly the same. So what we conclude from this is that, okay, so that means that my delta y is equal to thirds, right? And this is, this is what I was saying before about doesn't matter what your assumption is in the beginning, this is going to correct it, because now you know that this, the delta y in question, where is our delta y? The delta y in question is actually negative what we assumed. So it's not going to go downwards, it's actually going to go upwards. It's going to be something like this, right? Well, we always knew this intuitively, but now we can show this kind of mathematically. Let me get rid of this first. Whoop. And we can put this one here. Cool. Okay, so that's what we found out just now. All right, so now, but again, this is meters, by the way. What I can do now is I can plug that in here. Okay, so what I'm going to have is, I should have probably left more space for this, but I can just copy and paste and go downwards. Boom. Okay, so now let's put down the things that we know. 500, which is the left-hand side, has to be equal to minus 25, mass of B, gravity 9.81, acceleration of gravity. My delta y that we just found to be minus 2/3, plus mass of B, 25, velocity of B, over 2, plus mass of A, 30. I can go ahead and lose the 9. I'm going to have negative VB squared over here, over 2. Okay, and we're going to end up with exactly the same equation we had before, right? Because this is going to, if you multiply this, you're going to get the 163.5 we got before. It's going to be a positive number because we have negative times negative here. So that means it goes this way. Subtracting, we're going to have, by the end of this, 336.5 has to be equal to the same thing we had before, and that is 295 times VB, this. Let me think. Let me get this 3, this negative 3 here. It's negative 3, and let me take this out of the parentheses. So I'm actually doing this, and then this is equal to 9. So this is the 9 here, so I don't have to have this negative here, which means I can sum up the 25 and the 270 over here. So then, at least mathematically, this makes sense. So therefore, my VB, like before, is plus or minus 1.51 meters per second. But now, because we found out this is true, now we don't have to know intuitively. We actually know that VB is going upwards, which means that this is incorrect, and therefore VB is minus 1.551 meters per second, and it's going, upwards. Perfect. Okay, so this was all part A, right? So let's look at part B now. Where's part B? Where's part B? Part B here. What is the tension in the cable? So the tension in the cable, again, we could solve this just looking at Newton's laws, but we want to do this with an energy kind of point of view, right? Energy perspective. So how would we do this? Well, there's a couple ways, but let's think about this. If we have B, think about block B. Block B has 3 tensions upwards and it has the weight downwards, right? That's like the free body diagram of B. What I can do now is I can find out what's the resulting force on P, and I can relate that to the gaining kinetic energy, because the gaining kinetic energy is going to be a result of the resulting force on B. Okay, to do that, what I'm going to use is the following idea. Force is mass times acceleration, but we know acceleration can be written as the velocity times the derivative of the velocity changes with position, right? X. And we've done this in previous videos. You can check that out. But all I'm doing is I'm just relating, the definition of acceleration and the definition of velocity. Nothing fancy there. Okay. From this, I can say that F dx equals mass velocity dv, right? And what I can do now is I can integrate from x naught to x. It's going to give me the displacement in here from v naught to v. And I'm going to get, because my force is a constant again, and this is said quite clearly on the, where is it, in the beginning, in here, right? So just be sure. So that force can leave my integral, and I'm going to have my force times my delta x has to be equal to my mass, which is also constant in respect to the velocity, times my velocity squared minus my v naught squared divided by 2. Okay. Now, in our case specifically, the system is at rest. This is also clearly said in the beginning, so this is 0 for our case. And therefore, all we get here is that force times delta x will be equal to the mass times the velocity squared over 2. Okay, so the energy is going to be equal to the energy. Big news, right? But we can use this to our advantage if we're trying to calculate the tension. Why is that? Because the force from our free body diagram is just the weight of B minus 3t. And mind you that although I know already that my downward assumption is incorrect, I still need to keep consistent with what I've determined in the beginning, or else you can run into trouble. Okay, so what I'm saying here is that the sum of all the forces acting on the y direction on B is equal to the weight of B minus 3 tension. Okay, and again, tension is negative because this is what we considered in the beginning. Cool. So from this, what I can do is relate to the equation that we just derived from the bottom there. We can relate these two guys here. Okay, so where I have my force, I'm going to substitute by this, and where everything else I already have. So what I'm saying is that the weight of B minus 3 times the tension times my delta x, the displacement, is equal to the mass of B VB squared over 2. All right. Well, in the case of B, we know that our delta x is actually in reality our delta y because we're going in the y direction. It's really interchangeable. We could have just, over here said that this is dy instead of dx, and everything would be exactly the same. So I'm going to just quickly substitute here, so just so you know that I'm substituting, but nothing is changing, right? We know the delta y already. We already found it before. We know the mass of B. We know the velocity of B that we found before. So only unknown here is going to be the three tensions that we're trying to find out, right? So we can algebraically say that, okay, so that means that 3 of my tension will be just equal to weight of B minus mass of B, velocity of B squared divided by 2 delta y, and therefore my T is just, I can take, there's mass of B here and mass of B there, so we can say just mass of B divided by 3 that multiplies the gravity minus VB squared over 2 delta y, and there we just solve this for T and we're going to get our answer. So T equals 25 mass of B divided by 3, 9.81. Velocity of B that we found is 1.51, negative 1.51. The 2 is a constant, and then our delta y we found is negative 2/3. Okay, and these guys are very important because remember that these are related to our assumption of it being downwards. That's all. Yeah, that's all. So this is equal to approximately 96 newtons. Okay, unit-wise, let's just check. Here we have mass times second squared. That's meter second squared. That's an acceleration. Velocity squared. So that's meter squared divided by second squared. This is there's no units here, but here this is displacement. So this is meters. Okay, so we're subtracting these two, and that is okay because they're both an acceleration component. This guy 3 doesn't have anything. This guy is kilograms. So this is kilograms times acceleration, mass times acceleration, which is a force. So that's Newton. All good. Okay, so this is equal to Newton. Perfect. So that solves the part B of the problem. Okay. Now, before we finish, I actually want to show you that you could have done this with Block A if you wanted to, because it's exactly the same thing, right? Block A is also a system, like a component in this system. Block A, we have the 250 force over here, and the tension force over here. And for this case here, well, remember that our positive on the x direction is leftwards. So that means that my sum of forces, well, we also have, the weight of A here and the normal force here, but the sum of forces on the x direction, on the horizontal direction, is the 250, the positive one, minus the t, which is the negative one. And so the same thing applies, right? F dx equals mass of A, velocity of A squared divided by 2. So like we have everything, so we might as well just solve it here. So 250 minus t times the displacement for on the x direction was 2, positive 2, because leftwards is positive, equals mass of A, which is 30. Velocity of A that we don't have just yet, divided by 2. The velocity of A is just minus 3 times velocity of B. We've known that for a while. Velocity of B is minus 1.51. So this is just positive 4.53 meters per second. Cool. So 4.53 squared. Okay. Again, we can solve this. Over here, we're going to get, so I'm going to send this multiplying there. So we're going to have 4 multiplying there, so I'm going to have 1,000. 1,000 minus 4t. And this side here, I'm going to have 615 point about 22 or so, or 62, I should say. So therefore, t is just 96.095, so about 0.96. All right. And let's just do a last analysis while we're here, which is the following. Check out what we're doing on these two instances here. What we're doing is we're actually taking only the part of the energy, right? Only relating part of the energy. Because remember, the total energy given to the whole system is the 250 times 2. So it's a 500 joules, right? In this case here, what we're doing is 250 minus t, right? So that minus t there, so when considering the motion of A, that minus t there is what is going for the potential energy on B and the kinetic energy on B, right? That's the tension who's responsible for that. So if we take just this right-hand side here, if we just take the difference between these two guys here, the difference between, you know, the 250 and the 96, what we're going to have is whatever is used by A, and whatever is left from the 500 minus the whatever is used by A. Let's put energy by A, which is what, 192 or so, 192. The 192 is what we're going to be using for the kinetic energy on B and the potential energy of B. So the 192, let me just make sure my math is right. 500, yeah, okay, 192 or so, close by. That's going to be used for kinetic energy of B and then potential energy of B. Potential energy of B, we know that takes about 163. It's 163 from before, 60.5. So whatever is left, so 192 minus the 163 is 28.5. And then, like, check this out. And this has to work, or else we did some mistakes along the way. The 28.5 joules is the energy used for the kinetic energy of B. So that means that if I do this, okay, and I try to find VB again, doing 28.5 times 2 divided by 25 squared. Sorry, let's do this. Then I should get the 151 again. Cool, indeed I do. Okay, so positive and negative, we discard this one here, left of the. Okay, so this is just to show, like, there's all these different ways you can go about solving or understanding this problem. We did a couple different ways. So we did the general way that you're always going to get, you know, things right regardless of your initial assumptions. And we also did the intuitive way, which might be easier for some of you guys. Whatever works, as long as you know what you're doing. All right, I hope this was useful. If you have any questions, leave them down below. And if this video helped you out, just give a thumbs up, and we'll talk soon.